Hello, this is the classwork for the unit carbon packet that is useful in preparing for the gas laws test. So in the first 10 questions, they all use different versions of gas laws. I'm only going to talk through ones that are repeated. There actually is not one that deals with temperature and pressure, but the problem-solving strategies would follow the same sort of pattern here. So we got this little framework. So I'll review this as we talk through the questions. So every question gives a description of what's present in your system. So question 1 says you have 312 moles. Right away, if it tells you a number in a unit, you should see if you can figure out which variable that goes with. And since we know that moles measure amount, we put the 312 with the N. The temperature is given as 21.5 degrees Celsius, but we cannot use Celsius in any of the gas laws. This is the only unit you certainly have to change every single time. You have to change Celsius into Kelvin, and then it gives the volume as 2.1 liters. We know that's volume because it's measured in liters. The question asks for the pressure, so you literally write P and then identify that this is the thing you don't know. So what is the pressure in the atmospheres inside the balloon? So if all of these are given and we are asking for pressure in atmospheres, that even tells us which R value we would need. None of these variables are changing. It just asks for the current state. So it gives you these conditions and asks for the pressure. So that will be the ideal gas law. And the ideal gas law is PV equals nRT. And P, if you were to rearrange this question, divide both sides by V, you get P is equal to nRT divided by V. So then you substitute the values from the equation, you substitute the values from the problem into their variables in the equation, and you do your math, and from the calculator, you get this really long number. The fewest number of significant figures in the problem is 2, so your answer should say 3,600 atmospheres. That's an incredibly high amount of pressure. It's hard to imagine even a pressure that high. Okay, question 2 is asking us if a bubble has a volume at a certain temperature and this pressure. And then it says that the conditions change to STP. So it's helpful to review that STP stands for standard temperature and pressure. And so we have these conditions at the beginning, and then it asks for the volume at these new conditions. And standard pressure is 760 millimeters of mercury, and standard temperature is 273 Kelvin. And so if these are the 3 given at the beginning, and these are the 3 you need at the end, that would be the combined gas law. So P1 times V1 divided by T1 will always equal a constant value, so that P2 V2 over T2 equals the same value. So those two things must be equal to each other. And so if you rearrange to solve for the volume at the end, by looking at this equation, you would multiply by T2 and divide by P2. And so that's what we did to the left side of the equation. And after you pick the numbers, after you've converted, remember you can't use Celsius, put it in Kelvin. After you have made all your conversions, you've identified the equation, you take the values from the problem and substitute them in the variables of the equations, and you solve for 2.3 milliliters. Sometimes students ask if you need to convert milliliters. The only rule for the combined or Boyle's or Charles or Gay-Lussac's laws are whatever units you start with at the beginning are the ones you should end with. So if we started with milliliters, you should end in milliliters. It's possible to convert it to liters and then solve for liters. The only reason you would need to change into liters is if you are using the ideal gas law, which uses the gas law constant. And the units of the gas law constant are liters. So that's the only time you have to convert to liters. Okay, question 3 gives you an atmospheric pressure and a volume of a balloon, and it asks you to change the volume to standard pressure. So here's the values at the beginning, the initial pressure and initial volume. And here's the final pressure, and it asks for the final volume. So if it gives you P and V, and those are the things that change, that's Boyle's law. P1 V1 is equal to P2 V2. So the question is, what is the final volume? So you solve for V2 by dividing by both sides by P2. And then you substitute into the equation and solve for 99.0 milliliters, being careful to include 3 significant figures. So I'll review question 4, and then I'll just go slowly, and you can pause the video to review the work for questions 5 through 10. So question 4 says that you have a bike tire and it has a volume at a certain temperature. And then it says that the volume might change if the temperature changes, and so it asks for the final volume. So the volume that is given at the beginning and the temperature that are given at the beginning should be identified. Immediately, you have to change Celsius to Kelvin. You can't use Celsius in any of the gas law equations. So the question asks, what is the volume after the temperature goes up? So change it to Kelvin again. And if it gives you volume and temperature, and then those are the things that change, this is Charles' law, V1 over T1 is equal to V2 over T2. So then the question asks for the final volume, so we have to solve to get V2 all by itself. So we'd multiply both sides by T2. And then you can substitute the values from the problem into the variables of the equation. Solve using significant figures, and since there are 3 significant figures, your answer would be 4.02 liters. Okay, to review question 5, feel free to pause the video. Here are questions 6 through 8. Feel free to pause the video. And here are questions 9 and 10. Feel free to pause the video. Okay, questions 11 and 12 use the idea of standard temperature and pressure to help us convert between moles, or amount of substance, and volume. And this is true. At STP, 1 mole is always equal to 22.4 liters. So if you were to substitute 273.15 Kelvin and any of the standard pressures, like an atmosphere or 101.3 kilopascals, and whatever R value is assigned to those, you would always get V equals 22.4. So at STP, we can take the amount of gas and convert it into volume with this shortcut. We can go straight from grams to liters. Well, we can't go straight from grams to liters. We have to go to moles in the middle. So, but grams to moles and then moles to liters can show the units converting correctly. So grams will cancel, moles will cancel. And so 16 divided by 32 is basically a half. It is 0.5 times 22.4. So the final volume of half a mole of oxygen would be half of 22.4. So that's 11.2 liters. Questions 13 and 14 both deal with Dalton's law of partial pressures. Dalton's law says that gases exert pressure equally as long as the temperature is constant. The temperature of each gas is constant. So, for example, if the total pressure is 145 kilopascals, and you can figure out what percentage of the particles come from which gas, we know the total number of moles. So the percentage of oxygen molecules are 37.5%. 37.5% of the molecules are argon, and a quarter of the molecules are all carbon dioxide. So of all the particles contained in this container, we know that these are the percentages of each of them. And so for both argon and oxygen, since they both have the same percentage, I'm just going to do the same calculation twice. 37.5% of 145 kilopascals gives a pressure for each of these at 54 kilopascals. And a quarter of 145 is 36 kilopascals. So the pressure from each of them is directly proportional to the percentage of each of them. Now, this answer produces a final pressure that's like 144. It's due to the rounding error. All 3 of these numbers round down, whereas the remainder would have caused it to round up. So even though these are correctly reported to the right number of significant figures, it's just important to understand that there are often mistakes in rounding, and that's why we have some uncertainty in any measurement. Question 14 asks us to calculate the total pressure of the system and then the partial pressure in atmosphere in each of the gases. And so it's really helpful if we start by identifying the variables given in the problem. So if this is the amount of helium, and this is the amount of nitrogen, and this is the amount of hydrogen, you can start by identifying for helium. So helium is given. The number of moles are given. It asks for the pressure, but it does tell us the volume and the temperature. So those are all reported. And so you can calculate the partial pressure of helium in this size container at 3.4 atmospheres. Now, since nitrogen and helium have the same N value, like these two values are the same, that means they're going to have the same pressure. And then you use the same formula. Instead of putting 0.134 in, we would use the 0.0670 moles for the hydrogen, and that would give you a partial pressure of hydrogen at 0.43. So since we know the total pressure is equal to the sum of each individual partial pressures, 3.4 plus 3.4 plus 0.43, when rounded to the tenths place, would give us a number of 7.2 atmospheres. Question 15 is another Dalton's law, and it gives us a percentage of each chemical. And so methane is 77% of the container, so that means that 77% of the pressure is going to come from methane. Oh, this is, yes, methane. And then ethane, and then propane, and then butane. So in total, the pressure from the four gases that are identified is at 932, or 939.2, because this goes to four significant figures. However, there are other chemicals that are not accounted for, so the difference between the final calculated and the original initial must come from some other chemicals. Question 16 gives us an equation. So we have now stoichiometry that can help us determine how many moles of each product would be produced. And so it gives us an amount of water in volume. And because of the density of water, gosh, I love density. So density is always equal to mass divided by volume. And for water, the density is 1.00 grams per milliliter. And so if you're wondering what the mass of 14 milliliters is, you can use the density equation to solve for what number divided by 14 is 1. So that's how we get to 14 grams. And once you're in grams of water, then you can calculate the number of moles. Once you have the moles of water, you can determine how many moles of each product will be formed by using the stoichiometric ratio. Since this is 0.77 moles of water, almost 0.78. That means we're going to make 0.78 moles of hydrogen, and then half of that for oxygen, so 0.389. So the number of moles is determined by both the density equation of water and then the stoichiometry for the electrolysis of water. The rest of the variables are given in the equation, and so 5.15 liters and 0.777 moles of hydrogen are present. And then because we're reporting the answer in atmospheres, this is the R value we should use. The temperature must be converted into Kelvin, and then you can use the ideal gas law to determine what is the partial pressure of hydrogen. Separately, you would do the same process except now for oxygen. So instead of 0.777 for the N value, we'd use 0.389 for the N value. So you solve nRT divided by V for oxygen, and you get a number that's 2.03. And look, that's half. If the number of moles are half, the amount of pressure will be half. So after this process is finished, the total pressure in the container, after you have converted all of the water into hydrogen and oxygen gas, the total pressure would increase to 6.08 atmospheres. Questions 17 and 18 use gas stoichiometry again, just like Dalton's law in the question before. In this case, it gives us an amount of calcium, and it asks for the properties of the gas that's produced. So in this example, we have 0.075 grams of calcium. That means you're going to make 1.87 moles of hydrogen. Okay, so if you take calcium, add it to nitric acid, you're going to make some hydrogen. And now here's how much of it you'll make. N amount. So the N value is known. T must be converted into Kelvin. The pressure is given because it's the pressure in the room. And so that's the last question. What volume of the gas would appear in the test tube? So V is equal to nRT divided by P. So you substitute in the values in for the question, and then using significant figures, you end with 0.046 liters, but you can report this in milliliters. It sounds like we were using a small amount of calcium. We're going to probably use a test tube that is measured in milliliters, so 0.046 liters is equal to 46 milliliters. Question 18 gives us STP, and right away the shortcut between moles and volume at STP is that there is 1 mole is equal to 22.4 liters. In this question, it gives us the volume of a gas at STP, and it asks for the molar mass. So since we know that 1 mole is 22.4 liters, and here's the mass of the substance, so we know that density is mass divided by volume, and since the mole is the amount that we're using, 0.560 liters is 0.025 moles. Molar mass is measured in grams per mole. So if this is the mass of the gas, and here's how much of it you had based on the volume, we can determine that the molar mass for this particular gas is 62 grams per mole. So you take the grams per mole, those are the units for molar mass. Question 19 is a combination of Dalton's laws and the ideal gas law. And so it tells us that it's the opposite direction of electrolysis. This is the combination of hydrogen and oxygen to form water. And it gives you these properties. So the volume of the container, it tells us how much needs to be produced. So the amount of water that's produced is 0.84 moles. And that's the number you can use as N, because N is measured in moles. It asks for pressure, and it cites that the units should be atmospheres. So that's the R value you need to use. And temperature, again, must be converted to Kelvin. So P for hydrogen, nRT over V is 26 atmospheres. Because oxygen is half the number of moles of hydrogen, the pressure is 13 atmospheres. So the partial pressure of oxygen is 13. The partial pressure of hydrogen would have been 26. For water, we just take PV equals nRT, all of these values that were available. When you have these products produced, at the end, you had this much at the beginning. That's 39 total atmospheres. So we went from 39 atmospheres down to only 26 atmospheres at the end. And this should make sense. There are 50% more particles in this side of the product and in this side of the equation. So if the reaction exists in this state, the pressure should be 50% as high, 50% higher than the pressure in this part of the product. So if you were to calculate the total partial pressures, these are the values we went through using the ideal gas law. This final question in the packet is an excellent question for combining a whole bunch of concepts. It's no longer question 83 in the book, and in future versions, it's probably will not also be question 83. However, if this is the equation we're using, and here are the amounts, it asks for the partial pressure of this chemical. So, in order to solve this question, you have to determine which of the reactants is limiting. And so if we have two amounts of givens, so here's your reactant and here's your other reactant, you just produce how much product you could make from each of the given reactants. And so you can see ammonia by far is the lower number, so this is the limiting reactant. So in this case, that means you're only going to make 1.9953 moles of nitrous oxide, or nitrogen monoxide, which, when you round for significant figures, all of these values have 3, so the N value for NO, pressure of nitrous oxide, would be 2.00 moles. The rest of these values are given. 40 liters is given in the problem. Because the question asks for pressure in atmospheres, we should use this R value. Temperature must be converted into Kelvin, and you can solve for P. P is equal to nRT divided by V. So substitute the values in and solve for the partial pressure of NO is 1.61 atmospheres. The next question asks for the total pressure in the container. And so if you understand that the ammonia is the limiting reactant, that means that the oxygen is the excess reactant. There's going to be some oxygen left over. So if we were to draw a particle diagram that shows what chemicals would be present in this container after the reaction is finished, you definitely have some nitrous oxide. You should certainly have some water. But there will also be some oxygen that remains, because this is the excess. You would have made more NO than in the limiting reactant. So in order to determine how much oxygen there is that you remain, we know that you had 96 grams of oxygen. In order for this amount of oxygen to react with this amount of ammonia, we only needed 79.8 grams of oxygen. So we had 96. The stoichiometric ratio tells us we only need 79.8, which means there would be 16.2 grams of oxygen that remain. So when you convert 16.2 grams into moles, that's the number of moles of oxygen that are left over in this container after the reaction has finished. So we know that there will be 2 moles of NO. We just calculated that there would be 0.506 moles of oxygen. And we know that there are basically 1.5 times as much water. So when you use the numbers from the calculation, 1.9953 times 3 divided by 2, you end up with about 3 moles. And so all of these particles are going to exert pressure inside the container, and if you picked the total number of moles, that would give you the total pressure. So N total times R times T divided by V gives a final total pressure of 4.43 atmospheres. And that's all the group work, the class work, for the unit carbon packet. If you're using this to study for your test, good luck. If you have any questions, feel free to see your teacher.